cluster a whole lot of data in about the same time. 100 machines, divide that 20 microseconds by. Damn fast, not just real fast. So, check mark. That was the key thing, is to get speed up on the clustering and then get speed up on the search. Now, of course, the inner loop requires finding the nearest centroid. Remember, we're doing this to do find nearest points. Sadly, inside this, there's a find nearest centroid operation. We have a whole lot of centroids, like 20,000. Then you got to find that. So we've got to use a nearest neighbor algorithm inside this thing, which is facilitating an outer nearest neighbor algorithm. And I elect not to use the k-means searcher for that inner algorithm. That's where the projection search really comes in handy. We've tested both the projection search and the LSH search. The LSH search is not as fast, surprised me, as the projection search, with about 4 to 8 projections.
Do you require that your centroid be an actual data point, or do you allow putting a bounding box?
No, it's a mean of many data points. And it's a running mean of the data points that have been assigned to that cluster since the beginning of time. And so it would have started where the first one was assigned, but it might have drifted quite far away, and somebody else might have drifted quite close to that original point. So it could be a very bad assignment initially, but that isn't the issue here. It's just that the final result respects the original distribution of data, not that it respects the particular instance of data that we saw, just that it generalizes well. And so the 64-bit LSH gives us like 50x speed up in terms of the number of floating point operations that we need. But it's costly enough to do, probably in terms of memory as much as anything, that it doesn't actually win against projection search. You know, your mileage will vary. And there's more optimization to be done. I've done much more optimization on the projection search than on the LSH search. Moving to 64-bit LSH improved things massively. So we may go to 128 and see the course rates change. But it doesn't really matter at this point. Good enough is good enough. Better is just bragging rights. And so, as I mentioned, the Mapreduce implementation is easy. We just do the independent things. We throw them together. We get all the centroids in one reducer. If there's too many, we merge them the same way we merged before, and maybe change the thresholds and so on. And then we do that final clustering. We could use a combiner if we cared to, but I doubt it matters at all, because that final clustering is so small compared to the original data, and there's only one of them being moved around per mapper. It just doesn't matter. Yeah?
Did you check you have million data points, but what if you get like a billion, 0 billion, like how does it scale linearly, or is it?
Yes, it does, because it makes one step through each data point. Now, there's a log k, log of kappa. So kappa is in log k. No, yes, it's k log n. So the log of kappa is log of k plus log of n. And so there's a very weak dependence on the number of data points, log dependence on the number of data points you've seen. It does get slower, but log of it.
And
I don't
there's nothing shared between the threads.
No, nothing. Absolutely nothing. I just built a list of tasks and used the threaded evaluation.
And do run of the file-based matrix?
No, the file-based matrix is only for deploying a searcher. They don't use that. They just keep an in-memory list. Well, or a searcher actually, which if it's a projection searcher, is pretty simple. So yeah. So anyway, that's what we've got so far. I think it's exciting. I think it's going to be more exciting once it's more practical and it fits the standard APIs. It's a pretty simple API now, but it doesn't fit quite the Mahout API. And we need people to try it out and find out where it's broken. I mean, your question is good. That one can be answered by theory, but there's other questions about practicality. There's a very practical lady sitting back there, I think. What dimension did you test on? Things like that. She's seen real data. And so we need people to try this. But I think it's really exciting. And I'll
so I'm just missing something. This is a k nearest neighbor, not a 1 nearest neighbor, right?
The k nearest neighbor algorithm based on a k-means. Those are different k's.
Right. So if you first find the closest cluster, do you then find the k within that cluster, or if it goes to k?
You find a small number of nearby clusters,
Okay.
and that's a parameter.
Yeah.
There's an unfortunate number of knobs. You can tune a lot of these knobs, and I generally try to keep that down. But the number of clusters that you search is a knob.
Okay.
In the projection searcher, the number of random projections used is a knob. The number of things that you search nearby in each projection is a knob. There's probably not more than a dozen, maybe 2 dozen knobs total in the whole package. So that's kind of feasible, and most of them, you see what, you turn them up a little bit, and performance goes, woo, that's better, and then it just stops getting better. So it's really easy to adjust them. They don't do any weird shit. And the cost, like the number of projections, you have a list per projection, a tree set. So you know exactly what you're going to pay for each knob turn. It's not complicated. So, Macy's reappeared. I think it's hat time. Anybody want to see a stupid hat trick? Yeah. So, any more questions before we go to other things? So, yeah. Anything to avoid being social, right? This is a rude man. He asks me whether or not storm comes into this picture. That's the next talk. The next talk is where we do real-time online clustering, where data comes in, streams through, and at any point you can ask what the clustering of the data is so far. That would be kick-ass, huh? Yeah. Well, not in this talk. Wait till we actually.
Versus the talk.
Yeah, that's not been done. But it's quite clear that this algorithm allows that. Now you would pay every time you ask what the current clustering is. If you want a current rough cut, there's just the cost of moving data. If you want a current final cut clustering, there's the cost of the clustering of the rough cut every time you ask. No dumb questions. You have to ask.
For a certain point, you're doing it across many machines, and then you get more data. You take the model that you have.
So he asks if you have a model that you built on data so far, and you're happy up to now, but then you get a whole bunch more data because tomorrow is tomorrow and not yesterday. General principle there. Can you update it? It's an online algorithm, so yes, it's completely online. You could read those rough cut clusters back in and continue work. So yeah, that would only, of course, be useful in the storm implementation, which doesn't exist until tomorrow. Yes?
So actually there is no machine learning as such, right?
There's no machine learning as such.
Right?
I'm offended. The spirit of Alan Lapidus rules in his grave, whether or not he's in his grave yet. I haven't seen him for years. There was a fight, a good-natured fight that went on in the early 90s between Joan Farmer, who felt that machine learning should be learning, goddammit, you should have a small model, and Alan Lapidus, who had this devilish sense of humor. He says, look at this, let's just look at the data. He's a king or his neighbor. And every time there was a new data set, Alan Lapidus would show, bing, there's perfect performance on this nearest neighbor thing. Joan Farmer would go, rum, and he would tweak his learning algorithms. Back then it was backprop and so on, to do as well as Alan Lapidus had just done, in much less memory. So the question of whether or not nearest neighbor is machine learning or not is kind of an elitist thing. I mean, it's a machine that, given data, performs a task better and better as you give it more data. Now, the state gets bigger, yes. And so you might want to say that machine learning is only things which perform better in some super exponential way, that the state only gets log n bigger. I just care if the machine works. I don't care about, orthodoxy or religious qualifications on how it gets better, as long as I can afford the machine.
But I mean, it's good because you don't need to train anything.
Yeah, I mean, you do have to train it, because to get the k-nearest neighbor model that based on the k-mean searcher to work, you have to cluster the data.
Yeah, but it's not training, right?
It's not training with ground truth
Jeez,
data.
so fussy. It's unsupervised training. And you can turn it into a semi-supervised model or a supervised model just by including the target variable in the variables you cluster with, and then ignore it when you're classifying. I mean, there's all kinds of ways. There's training going on here. Give me a break. It's just big. It's big state. That's the only badness here. And if you have clusters that are purely one state or the other, then you can start dropping them, and it turns into an SVM algorithm. And it has log size, log of n size. So yeah, you can do it any way you like, but it counts as machine learning. Don't do that now. Sorry to sound petulant. Anything I work on for this long has to be machine learning. Come now. Any other questions? Nobody will risk losing a hat. Come in, you can ask. Okay. Well, let's do something. You ready? What do we got?
So, did everybody get one of these pamphlets here? Inside there should be a number in the middle fold. This was a statistical conference, so we should do. To write in the number that we're going to call? Okay. Can I have number 48? Are you here? Yeah.
We should get back to the nearest neighbor.
Yeah, nearest neighbor. 35.
There you go.
Yeah. That's more random. Do you have anything 27?
Come on, such a nice number. 27.
27.
There you go. Better look this way.
Good catch.
Okay, anything higher than, what, lucky 100?
I'm over 100.
Over 100?
Yeah, look.
That's close enough.
Thank you. I should ask for an autograph.
Or you should come late more often.
Okay, I haven't seen any numbers on this side of the room, so this must be clustered on the left here. Let's try 76.
This is not a random algorithm.
No 76. 89. 14.
Oh, nice.
How close?
Very good.
Okay, try to guess your numbers now. 54. Hey. Okay, what's the temperature of this room? in Celsius. Okay, have we got a 53 here? Oh, yeah. We got number 7, lucky 7.
Oh, how did 7 get back there?
Look, everybody's on this side, guys. Number 2? Alright. There you go. What have we done? 3. We're waiting for number 1 here, right? Yeah. Hey, we still got a lot more hats.
By the way, I have to make a comment that among children, this does not mean the number 1.
Let's go into the teens. How about 13?
I love prime numbers.
Let's go another prime number, 17. Six.
That's like much bigger.
Number too small.
Okay. 73, we haven't solved. No,
There's no 73.
73. Are the looking through the
Oh,
crowd here.
3, come on. Let's think back to those Russian computers.
91.
Higher.
Higher. Lower.
Price is right.
Lower, 81.
Magic number 42.
42.
Yeah.
Long
There
throw. No good. Let's try this again. Here you go. You ready? Oh, he doesn't want me to try again. Some skills, yeah.
That's like that, it's not.
All right. 27.
81.
81.
81, the next power of 3. No powers of 3 in here.
I don't like even numbers, so that's the problem.
Powers of 2. Pick an even number to order.
16.
Plus 2.
The hexadecimal kid speaks.
Oh my god.
And his faithful dog asks him, remember that? There's no 16.
All right, I haven't called any 60s yet. How about 62? All right, in the
So
back.
crazy.
All right.
An even number. This is not the last one.
Oh, we got plenty more.
Incredibly.
Yeah.
Oh, that's it. Okay. 5 more magic numbers.
How about we just let the happy thing? Ready?
Ready, guys?
This side, this side. Farther. That is higher.
There you go.
So, please just send me emails, hit me on Twitter, give me a call, let's do something. We won't want to get into Mahout for a couple months, but, it's there now.